Greetings. My name is Ramesh Garimella. I'm an associate teaching professor at Drexel University. I'm excited to be here to make presentation on basics of cryptography. Before I begin, I would like to thank the Delaware County Community College and also STEAM Speaker Series Coordinator, Dr. Elias Argyris, for giving me this opportunity. So let me outline my presentation first. What is cryptography and why is it important? And I will highlight some encryption and decryption schemes, and these are based on modular arithmetic. Particularly, we'll focus on three classic encryption schemes. Those are Caesar cipher, multiplicative cipher, and affine cipher. And these are not secure anymore with advent of fast computing capabilities. The RSA encryption, the last one, is widely used. So before we dive into these things, I want to introduce some necessary number theoretic tools for encryption. At the end, I will demonstrate a live Python code, which I got from Google Colab. So let's get started here. What is cryptography? When conveying a confidential message, how can we ensure that it can only be retrieved by the intended recipient? For example, all of us engage in e-commerce on a daily basis. We share our credit card information, we share some of our personal information. Sometimes even we share social security numbers when applying for loans. How secure these communications are. And I don't have to tell you how important it is to send secure messages during a military warfare or some diplomatic messages. So these are all important things. Cryptology is the discipline dedicated to crafting and decoding secret messages. First, some terminology so that we all are on the same page. Plain text. Plain text is the text intended for secret communication. I will use this throughout the presentation. Encryption is a scheme. How you transform your plain text message into a secret message, also known as ciphertext. So ciphertext is the text derived from the plain text using an encryption scheme or method. So this ciphertext may be actual text in English language, which may not have any sense, which may not make any sense, or it could be a string of numbers depending on how you encrypt the message. Decryption is the reverse process of encryption so that the recipient can turn the ciphertext back into plain text. So these are some basic terminologies that we will be using throughout this presentation. Now, as mentioned before, in this presentation, we will focus on 4 encryption methods: Caesar cipher, multiplicative cipher, affine cipher. These are classic ones, give you a flavor of type of encryption, and RSA is widely used and difficult to crack. There are other encryption methods. There are numerously many, but we won't talk about them. So some basic math relevant to encryption. So we always fix a positive integer known as modulus. And we try to do addition and multiplication using modulus in the following way. We say two integers a and b are congruent mod A is congruent to B mod M if the difference is divisible by M. For example, 27 is congruent to 7 mod 5 because 27 minus 7, which is 20, divisible by 5. Also, 7 is congruent to 2 mod 5 because the difference between 7 and 2, which is 5, is divisible by 5. So what it means is when it comes to mod 5, there is no distinction between 27, 7, and 2. We do modular multiplication in a similar way. I'll explain that in a later slide. In the following, throughout our presentation, we're going to use the modulus to be 26. You may ask why 26? Because there are 26 letters in the English alphabet. So let's perform some addition and multiplication of numbers using modulo 26. So here are some examples. Let's say I want to compute modular addition mod 26. So how do I add two numbers A and B? So first thing is add the numbers A and B together and take the remainder when dividing the result by 26. For example, how do I add 17 and 22 modulo 26? First, add 17 and 22, which gives you a total of 39. Now divide 39 by 26. 26 goes one time in 39 with a remainder of 13. So that 13 is the sum of 17 and 22. So that's how we add two numbers modulo 26. So let's say we want to perform multiplication of two positive numbers A and B. First multiply the numbers together, A and B. So there's a typo here. There's no need for this N here in this statement. Take the remainder when dividing the result by 26. So here is an example. So I want to multiply 7 and 5. Remember, modulo 26. So multiply 5 and 7. The product is 35. Now divide 35 by 26. 26 goes into 35 one time with a remainder of 9. So the multiplication of 7 and 5 is 9. Next, here are some numbers that are significant for us among 1 through 26. And those numbers 3, 5, 7, 9, 11, 15, 17, 19, 21, 23, and 25. These are called multipliers mod 26. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of course, I'm not counting 1. You could, if you want, you could add 1 to this list, but 1 is not really useful for us. So these numbers, what do they have in common? All these numbers, 3, 5, 7, 9, so on and so forth, these are relatively prime to 26. What it means is there are no common divisors between these numbers and 26. And also note that 3 times 9 is 1. So because 3 times 9 is 27, that leaves a remainder of 1 when divided by 26. 7 times 15 is 1. 5 times 21 is 1. 7 times 23 is 1. 11 times 19 is 1. 25 times 25 is 1. So this list of numbers, 3 to 25, when you multiply one with another, you get 1. And one of them, 25, multiplied by itself gives you 1. Again, the multiplication is done modulo 26. Some special comments about this multipliers. So 3 times 9, as observed above, 3 times 9 is 1. So 3 and 9 are known as multiplicative inverses of each other. 7 and 15 are known as multiplicative inverses of each other. So are 5 and 21, 17 and 23, 11 and 19, 25 is a multiplicative inverse of itself. And these play an important role, a useful role in multiplicative and affine ciphers. Now, with that background, mathematical background, I'm going to introduce you Caesar cipher. So first thing is a table of reference. Here you have letters A through Z, lowercase, and each letter is assigned a numerical value, starting A with 0, B with 1, C with 2, and so on and so forth, Z with 25. Now fix an integer k in between 1 and 26. Usually we don't take 1, so take somewhere between 2 and 25. It is called the key or a shift. So in Caesar cipher encryption, the numerical value of each letter in the cipher text is determined by shifting the numerical value of the corresponding letter in the plain text by k. Of course, the addition is done modulo 26. So let me repeat that. So you have a plain text. You convert each of the letters in the plain text to a numerical value as listed in this table. And then each of those numerical values shift by a key, a number k. This k is in between 2 and 25. And when you shift, you have to do the addition modulo 26. And whatever you get, numerical values, you convert them into text using the same table. So that would give you cryptic text or cipher text. For decryption, you have to reverse the process. So you take the numerical value of each letter in the cipher text and shift it back by the same key. Shift it back means you have to subtract and then do mod 26. You get your plain letter, plain text back. So that's the process of Caesar encryption. So let's look at a simple example here. Again, I put the table up there for reference. So here I'm going to use the key k to be 12. So 12 is in between 2 and 25. So let's say the plain text is how are you with a question mark. I want to convert this into a cipher text. First thing is we need to clean up plain text. What do you mean by that? So when you have a message, we first drop all the punctuation marks, we delete all the spaces, all the special characters, and that's what we call plain text. I'll talk more about it later when I do a Python demo. So for us, the plain text is how are you with no spaces, no question mark. That is all lowercase. Now, if you assign the numerical values, notice that H is 7, O is 14, W is 22, and so on and so forth, U is 20. How did I get these values? These are taken from the text, from the table above here. Now what we do is to convert this plain text into ciphertext to each of these values, 7, 14, 22, and so on and so forth. You add 12 and you compute the sum modulo 26. For example, 7 plus 12 is 19. It stays as it is. But 14 plus 12 is 26. 26 modulo 26 is 0. 22, you add 12, you get 34. 34 modulo 26 is divide 34 by 26. It goes one time, with a remainder of 8. So that's how I got these numbers 19, 0, 8, 12, 3, 16, 10, 0, 6. These are cipher values. Now we want to convert the cipher text, convert it to cipher text. So go back to the table above. 19, for example, from this table, we see it is T, 0 is A, 8 is I, and so on and so forth. Therefore, for this plain text, how are you? Using the key 12, the cipher text is TAIMDQKAG. So this is a statement, a sentence, a text, which has no meaning, if you, gibberish, but it corresponds to how are you. So the person who receives this, they know the key. So they take each of these numbers 1908, subtract 7, and do the modular arithmetic. So when you do the modular arithmetic, you'll get those numbers 7, 14, 12, 0, 17, and so on and so forth back. And then if you convert that back into text, you get how are you. So this is how the Caesar cipher encryption is done. What happens if the text is very long? So the Python can easily do all these calculations quickly. So I'll talk about it toward the end. Okay. Now, the next cipher is called multiplicative cipher encryption. Again, I listed the table here, lowercase a to z. Again, numerical value 0 through 25. Now, it's a multiplicative cipher. I'm going to take the special multipliers I listed in a previous slide. And remember, the multipliers are 3, 5, 7, 9, 11, 15, and so on and so forth, and 25. In the multiplication cipher, unlike in Caesar cipher, which is an additive cipher, here we take numerical value of each letter in the plain text and multiply by this multiplier k that you chose. And again, the multiplication is done mod 26 to get the cipher text values. And for decryption, what do we do? As you may recall, we noticed that if I take k to be 3, the key to be 3, 9 times 3 is 1. So you got to use 9 as the inverse key to decrypt the message. If I use key to be 5, as we noticed in the previous slide, 5 times 21 is 1. So we're going to use inverse key for 5 as 21. And for 17, likewise, the inverse key is 23. So we know that each number in this list has its inverse in this list. And you might remember 25 is its own inverse. So if you multiply each letter by 25, again, to decrypt, you multiply by 25. So here is an example. Again, I'm using the same plain text. So to illustrate the differences between various encryptions. Here I took key to be 9, number 9. Notice that the key comes from this special multiplier list 3, 5, 7, 9, so on and so forth up to 25. So again, my plain text is how are you? And you have to clean up the text without any punctuation marks, lowercase letters. So here's how are you? Now, just like before in the Caesar cipher, I listed the numerical values of each letter in the plain text. How are you? H is 7, O is 14, W is 22, all the way U is 20. Now to get the cipher values, I take each of these letters and multiply by the key 9. And again, the multiplication is done modulo 26. So when I multiply 7 by 9, I get 63. 26 goes into 63 twice with a remainder of 11, so that 11 is the product of 9 and 7 mod 26. Likewise, 22, 16, 0, and so on and so forth. So these are my ciphertext values. You convert them back into letters using this table. So 11 is L. You can see that from this table, second row, 11 is L, 22 is W, 16 is Q, 0 is A, and so on and so forth. Therefore, your ciphertext is L, W, Q, A, X, K, I, W, Y. So same number of letters as your original text here. And this is your ciphertext. If somebody gave you the ciphertext and told you the key is 9, then the key to decrypt is, remember, 9 times 3 is 1. So the multiplicative inverse of 9 is 3. So you got to take these numbers, 11, 22, 16, 0, 23, and multiply by 3 mod 26. If you do that, you get these numbers back, 7, 14, 22, and so on and so forth. Now convert them back into plain text, you get your plain text back. So that's how you encrypt and decrypt using this multiplicative cipher. Okay, I hope we are doing good so far. Let's move on to the next cipher, which is known as affine cipher. So affine cipher is, we are combining the Caesar cipher, which is additive cipher, and then multiplicative cipher. So somehow we combine these two. To do so, we need two letters now, or two keys. One key is called K1. That's an integer between 2 and 26. We use this to shift, like in Caesar cipher, Caesar encryption. And K2 is your multiplier. Remember, K2 can only be one of these numbers, 3, 5, 7, 9, 11, and so on and so forth. So we got to have two keys to convert a plain text to a ciphertext using this affine cipher. So what we do is, just like before, we take the plain text and multiply each letter by the key K2. Again, the multiplication is done mod 26, and then add K1, the key. So you don't have to do two separate calculations. So you could take numerical value of a plain text letter, multiply by K2, the multiplier, and then add K1, the shift key, and then compute modulo 26. So that's how you get your ciphertext. If you want to revert it back to the plain text, instead of multiplying each letter by K2, you got to multiply by its multiplicative inverse. So as I mentioned before, if I pick K2 to be 7, the multiplicative inverse is 23, because 7 times 23 is 1. So take your ciphertext, multiply each letter by the multiplicative inverse of K2, and then subtract K1, and then do modulo 26, you get your plain text back. So that's how you combine Caesar and multiplicative cipher to get affine cipher. So here's the same example as we talked about before. So here again, the table of all lowercase alphabets, assigned value 0 through 25. Here I'm taking the shift key to be 12. I think I used the same thing before. K2, this multiplicative key is 9, which is among this list 3, 5, 7, and so on and so forth. And keep in mind, for 9, the multiplicative inverse is 3. So again, I took my plain text, cleaned it up, and wrote down the corresponding numerical values 7, 14, 22, 0, 17, 4, and so on and so forth. Now multiply each of these numbers by 9, which is a multiplier, and then add 12, and then compute mod 26. So if you do so, you're going to get these values. So 7 times 9 plus 12 modulo 26 will give you 23. So you get these cipher values. Now convert that into ciphertext. It is XICMJWUIK. So you get some letters. So this is your ciphertext corresponds to how are you using the affine cipher with keys 12 and 9. So if somebody gave you this, you need to know the key to go back. So going back is you take these numerical values 23, 8, 2, and so on and so forth. First multiply not by 9, but multiplicative inverse of 9, which happens to be 3. So multiply each of the letters by 3 and shift it back. That means subtract 12 and then compute modulo 26. You get your 7, 14, 22, 0, 17, so on and so forth. And that is your plain text. That's how you go back and forth between um, plain text and ciphertext. So I gave you 3 examples, and these are classical ciphers. They're not secure anymore because anybody can break this. The possibilities are just few. So this is just for illustration purposes to understand the concept, but real and do it for fun, but not really to send messages, secure messages. So the next thing is RSA encryption. It's also known as public key cryptography. This is widely used today. What does this RSA stands for? It is the initials of the last names of the mathematicians, computer scientists who invented this method. Revest, Shamir, and Edelman, all of them were from MIT, who came up with this method. So first, let me describe this method briefly and then illustrate it. So in this method, you have 2 large prime numbers. Remember, a positive integer is known as a prime number if it has no divisors other than 1 and itself. For example, 3 is a prime number. 5 is a prime number. 11 is a prime number. 15 is not a prime number because it has 3 and 5 as divisors. So you take 2 prime numbers, but not any 2 prime numbers, really large prime numbers. Typically, each one will have at least 300 digits. 300 digits, let me repeat that. And then compute the product of those 2, and typically you're given that product. And to break that product into product of primes P and Q, it is almost impossible. Computer will take years and years to compute P and Q. So it is not possible. That's why there's need to invent new prime numbers every day. Even though by theory there are infinitely many prime numbers, we are still computing, we are trying to discover large prime numbers. Now the next thing is, take a number E. This number E has this following property. It got to be in between 1 and P minus 1 times Q minus 1. And again, they know P minus 1 times Q minus 1 because they know people who encrypt using RSA, they know what P and Q are. So you take a number which has no common factors with P minus 1, Q minus 1. The question one might ask is, why do you need to pick something like this? This has to do with some sophisticated number theory. And it tells you this kind of E has multiplicative inverse. Just like I mentioned before, 3, 5, 7, 15, and so on and so forth, they have multiplicative inverses modulo 26. This number E has multiplicative inverse modulo this huge number, which product of P minus 1 times Q minus 1. This pair, the number E and number N, these are called public key, and it is known to everybody, to the public. Then D happens to be the multiplicative inverse of E mod P minus 1 Q minus 1 serves as the private key. So here it is mod P minus 1 Q minus 1 serves as the private key, and it's known only for intended recipient. Nobody else knows that. So this D is, again, there's a typo here. This D is the inverse of E mod P minus 1 Q minus 1. So here's how this RSA encryption works. So first thing is you take your plain text message and take each letter. So you have alphabets ABC, we have numbers 0 through 25. Take each number, each letter, we call it M, plain text letter, raise it to the eth power. So you are computing a large power of the number modulo N. N is P times Q. And then that will give you a numerical value, and you list these numerical values as your ciphertext. So in RSA encryption, the ciphertext happens to be string of numbers. Now, once the person who is supposed to receive this message, they get these numbers, then what they do is you take each number, raise it to the dth power. Remember, D is multiplicative inverse of E. So when you raise it to dth power, it becomes a letter, and you get a numerical value. And then for these numerical values, you convert them back into plain text. So that's how you do RSA encryption. So finally, as I mentioned, I'm going to utilize Python on Google Colab to demonstrate various encryption methods. And this Google Colab is a freely accessible software, and one has to learn how to write the code. So let me illustrate that. Before I do the illustration of Python, I referred to a couple of textbooks, Elementary Number Theory by Ken Rosen. There is a chapter on cryptography. So there are lots of other techniques. And also, you might want to consult with Cryptography and Introduction. This is published by American Math Society, and editor is Eschenko.